Yes. Our apologies. Book has an error in it. Correct answer is posted. It's a new book, so you do need to give Guy a little slack. Howdy, if you would just give it to him, I'll tell him what to do with it. No name. All right, which jerk handed in this paper? It's worth something. But it says no name, -9. Pass that around if you would. Can you catch it? I'm sorry. I thought sure you could catch that. If you would, thank you, ma'am. If you would, hey, you ready to start class? You are? You sure? All right. Well, I don't want to disturb you now. I understand you had a hot date last night and comparing notes. If you would, take the homework, pass it from there, down to, back to, over to, back to, down to, over to, back to, over to, down to, over to, back to, back to. If you wouldn't mind, haul it over to him. Either that or throw something at him, he'll come pick it up. Across, 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 across. That way everybody ought to get. What are you eating? You didn't offer. Can I have one? No. Is there any left in there? No. Okay. I'll wait till you finish. I didn't really want one. And whenever y'all end up with it, if you throw it back up here. If you see anybody sitting on a desk next to him because that guy didn't show up for class and he's too lazy to pick it up or he's sleeping, all you got to do is you just leave it there for a few minutes and then bring it to my attention, and I will grade his quiz so hard we'll have an extra 5 points left over, and I'll give them to you. Just point to him, okay? The problem is if that thing gets left in here, nobody knows what to do with it, and so somebody throws it in the trash. And then nobody up front here gets their homework. So please, be sure you pass the homework on down to the next guy. Sorry about the mistake in the homework. Don't wait till the last minute. The first I heard about it was this morning. I didn't know it was an error, so I posted it as soon as I could find it. But really, work on these things early. If you wait till the last minute to come and get help, you probably won't get any help. Anybody got any more homework that you're back there copying from somebody? Because it's only going to be, yours and his is only going to be worth half. Okay. Now, while my back was turned, I haven't taught this class in probably 8 years. Oh, we found out whose it is. Okay. At least someone claimed it. It may not really be his, but has tried to turn it into a statics class. So we're going to do a little review of the things you know you should already know, like trusses and shear moment diagrams, but we're going to go through them pretty fast. So if you really had a bad 221 prof, I think a lot of you raised your hands last time. You need to come see me for a review on this material because everybody else doesn't want to have to mess with this. A short, brief, just so you know, I've never seen anybody try and build something like this, so I don't really think that you have too much worry, but in your text, you should be able to tell if that is a statically determinate structure and if it is stable or unstable, and you really ought to do it, I think, just about as much by feel as anything. Just counting joints and counting members and counting special conditions, works a lot of the time, but sometimes those equations can mislead you. You should know this is a cantilever beam. That's all it is. It just sticks out of the wall. They hold up nicely. You can imagine. Then all of a sudden someone came and added how many forces. Not how many reactions or not how many pieces of steel, but how many forces. One is correct. So they put a roller underneath it, which causes one vertical force. Then on this end, they put a pin, which caused 2 more forces. And so this is statically indeterminate to the 3rd degree, because it was fine as a cantilever till somebody started putting all these extra supports on it. Now these extra supports are very useful. They make the structures much safer, because if it does fail as a cantilever beam, it just falls in the water. But if it fails with it supported on these other pieces out here, you'll know it. It'll get a lot of failure in this area, and there'll be plenty of time to get off of it. So statically indeterminate structures are often made that way because they're very efficient, and also because they're much safer than statically determinate structures. There's a backup to a potential failure. This is nothing but a simply supported, hey, yeah, that's right. This is nothing but a simply supported beam with an overhang. And then someone took a thing that looks like that, which is not stable. You see it won't fall up and down, but put some loads on it, and there's a good chance it will rotate about that pin to prevent the left end from moving up and down, and therefore to prevent rotation around the pin. He hinged it to something that's stable, and he's turned the whole thing into a stable structure. For this one here, that would have stood up nicely as shown. Wouldn't have needed anything else. It'll just stay there. Be a nice little roof structure. You can put it next to a bus stop and get underneath it. It's fixed to the ground. And then someone came and added 2 forces. By adding 2 forces, they made it statically indeterminate to the 2nd degree. This one here was a nice pair of cantilever beams, and somebody came in with a filler beam in between there, and had they hinged the left end of the filler beam on the left end, it would not have moved up, down, or left or right because of the hinge. And then the right end would have flopped down to the ground until they added this right hand hinge. And at that point, it's going to be statically indeterminate in the axial direction, because if I were to put a force on here like this, you really wouldn't know how much of it came out this end and how much of it came on down through this and came out through this end. So just like it is statically indeterminate to the 1st degree. Now he could have prevented that by putting a roller and then putting the beam across the top like that, and then hinging it to this. That would have left this just as a simply supported beam by itself without any axial capacity. Then you could have driven on the beam, you could have driven on the beam, you could have driven on the beam. And I'm not saying you'll get all of these right away, but you get a feel for them, and they're not that bad. By hinging it on the 2 ends, it's statically indeterminate in the 1st degree before this guy comes around and messes with it. And the next thing is he came and he decided to put some more supports on it. He put 1 more support, so it ought to be statically indeterminate to the 2nd degree. How about this one? What do you think about that structure? If you push on it to the right, what do you think would happen to the hinges? They'd rotate. It's just that simple. Once you put a load to the right on it, this thing says, well, is it okay if I do this? And the guy says, well, no, you can't do this unless it's okay for me to move to the right. And he looks down here, and this guy says, it's okay with me, you want to move to the right. That's no problem. And so it is unstable. Have I ever seen anybody start to build one of those and then say, oh, wow, let me see if it's unstable and so I won't build it? No. And that's pretty unusual. Usually what you make is you make these things here. Or you make these things here. Thank you. That's usually the kind of things you do. Then just start taking things off and see what's left. If I didn't have anything but that, would you tell me to duck? Well, I would hope you would. You may not, but I would hope you'd say that's not stable. The right end is nicely supported, except it can move left and right, and the thing could rotate about that point, so no, that's not a safe structure. So somebody decided to do this to it. That at least keeps it from rolling about this point. Axial force is in here. However, it's still possible if you push to the right, the link would roll to the right, and then that axial force could not be taken because of the roller. And the guy says, well, you haven't let them see everything yet. Well, okay, that's true. But right now, it's still unstable. And now then, here's that last force we're looking for. Horizontal forces through here will go through here. Will not go through the roller because it's a roller, but will come down here in tension. And here's just a plain old beam, simply supported beam. The right end of this simply supported beam is supported on something that won't move up and down. And the thing that could sadly move left and right can no longer move left and right. Statically determinate, and it's stable. There's a truss. Probably the simplest truss on earth. And it won't fall down. You've seen trusses forever. And so somebody came in and added another member to the truss. This thing was happy to stand as it was before you put in this additional axial force. And so you are causing it one more reaction. So you are causing one more degree of indeterminacy if there was any in the first place. There wasn't any in the first place. Therefore, you've added one. Wouldn't take you long to figure that out. Once you cut this hinge in order to some forces vertical and some forces horizontal, you'd say, I got a problem here. I have two equations and I have three unknowns. And so it is statically indeterminate to the first degree. That one would stand up by itself. It's hinged and it's got a pin. The truth is, if you would even change that to a roller, it would be okay, because when you put loads on top of it, it would tend to roll down, except this guy wouldn't let it. And as you start adding things to it, then you're going to add degrees of indeterminacy. So when he changed that to a pin, it became statically indeterminate to the first degree. Then this one, it was okay because it was pinned. If you say the roller might lift off the ground, remember that these rollers are made so that they can take tension. This is nothing but a convenient way to show you that the support is purely vertical. It'll take tension or compression. Then when you put them together, you make it more degrees indeterminate. It's not hard to see if something's indeterminate, because once you try and solve for the forces, you can't do it. That tells you right off the bat it's statically indeterminate. Some of those kind of structures we'll analyze by hand. Others, as they start getting ugly, you just don't have much choice but to go to a computer program and let it analyze the problem for you. So, enough of that. We'll talk about more statically indeterminate structures later. Trusses. Two basic ways to solve for the forces inside of a truss. Oh, thank you. Big time hay. Okay. Here's a truss. Typical. I'll leave it for you to solve for the reactions. A lot of times they'll show you the distance on each one of them. Sometimes they'll merely say 1, 2, 3, 4, 5, 6 at 15 meters. And you're supposed to know that that's 6 equal panel spacings at 15 meters each. Height, 20 meters, not drawn to scale. The first method of analysis you were taught for trusses was method of joints. Hopefully it was impressed upon you that cutting out joint J at this time was a futile exercise. Because in order to isolate the piece of steel, the little pin at J, you cut through 1, 2, 3, you cut through 5 members, thereby exposing 5 unknowns. May be useful later on, but at this time, too many unknowns. At this point, it is futile to cut out joint B, because in order to isolate the piece of steel at B, you had to cut through 3 members. Those 3 members all have an unknown force in them. You only have 2 equations of statics, some forces horizontal and vertical. You've lost your sum of your moments equation because all the forces go through point B. So plan on it. If you want to use the method of joints, you'll have to cut out a joint that has no more than 2 unknowns coming into it. If you've already worked this number from earlier work and this from earlier work and this because it's a zero force member, then you could solve for these 2 by method of joints because you only have 2 unknowns coming into the joint at that time. The reactions on this structure, as I say, I'll leave that to you. 400 kilonewtons and 200 kilonewtons. And the reason I know that is because this is 4/6 of the way over to the support, and so this is 4/6 of the load, and the same way in reverse. But you're more than welcome just some moments about A to find the answer for those reactions. That tells me that quickly I probably have the ability to solve for forces in the members entering this joint because there's only 2 of them, or this joint because there's only 2 of them. For no reason whatsoever, I'm going to tell you I'm looking for the force in member FG. In order to solve for the force in member FG, you must cut member FG, thereby exposing the force in that member. Then you go ahead and cut around the joint, cutting as few additional members as you can, and cut through the reaction, and cut through any external loads, the lines of gravity through those loads, and isolate the joint. Here's what the joint looks like. Joint G has a cut steel piece and a cut steel piece and a reaction. 400. The slope of this member needs to be shown on the member, either here or on the original drawings. It needs to be somewhere. It has a horizontal slope of 15. It has a vertical slope of 20. So that's a 3, 4, 5 triangle. This is horizontal, so I don't need to show anything on it. As soon as you cut through the piece of steel, you need to put an arrowhead on the unknown. That's normally a guess. Sometimes you have better guesses than others, sometimes worse. Crawford, which way do you think it goes?
Pretty
No. Even though it tells rule. I know, I do too. But I'm okay because as long as I'm talking, I don't nod off. Also, I've already passed this class. And it has been guessed intention, and that may be wrong. And if you hand in your homework as soon as you walk in, it's not considered late. If you sit back there and copy from somebody, it's considered late. Now then, I'm going to guess that the force in this member is also tension. And it's a pure guess. Right or wrong, I don't know. I mean, I do know, and I think you know too. But and if you say those are some pretty bad guesses, yeah, but I want to make sure you know what to do when you don't know what to do. Just have to guess and put some arrowheads on there. I get all kinds of students who I say, how come you didn't work the problem? Well, I didn't know which way to put the arrowhead, and so I didn't want to get it wrong. But I didn't know which way to put the arrowhead. You got to put the arrowhead. When you sum forces vertical, you got to commit. I say it goes this way. If you're wrong, your answer will come out with a minus sign. The minus sign won't mean it goes down, left, right, up. It won't mean anything except you're not a very good arrowhead guesser. Put it on the other end. And it has to have a name. Probably a reasonable name for the force in that member would be FG. You can call it dog, but it's a little harder to figure out where it belongs. And this would be HG. It has to have a name. Especially in this class, you'll be doing a whole bunch of these. And people who say, well, I've got 4 free bodies there, and I used this one for a while, then I went over to that one, then I came back to the first one, and then I went over there. And I can't follow your work. If the answer in the box is right, you get full credit. If it's wrong, you get nothing. When you bring your paper up and say, look, I only have one little mistake. I took the horizontal component of this as 20/25 by mistake. Well, sorry. You need to tell me, hey, boss, yes, I'm using free body number 1. It's okay with me. And my first equation reads, and then if you get down somewhere and you get an equation that doesn't do you any good, you can't proceed, and you move to another free body, then you tell me, equation 8 is using a new free body. Then I can follow your work step by step. Where you make a mistake, I can take off a point or two is all I'm going to get. And then I would assume that everything you did from then on is not incorrect, based on what you've already paid for. You can sum forces horizontal or you can sum forces vertical. If asked, would you like an ice cream cone now or would you like it in an hour, most people would rather have it now. And me too. Which equation would you prefer, sum forces vertical or sum forces horizontal first? Vertical. And the reason is it gives you an answer immediately, and that always feels good rather than waiting. Yes, you can sum forces horizontal. Yes, it'll be useful later. But there's only one guy's got a vertical up and down component to it. Only one unknown. So I would suggest you sum forces vertical is equal to 0 is equal to plus FG. And then you say, well, now wait a minute now. I'll admit FG kind of goes up, but all of FG doesn't go up. Just a piece of it goes up, and that is correct. Only 20/25 of it goes in the vertical direction. Plus the reaction is 400, and therefore you can solve for the force in member FG is equal to minus 400 times 25 over 20, 0, 0, that's 2 into 40 is 20, 20 times 2 and 25 is 50, so it's 500 with a minus sign. Now what you do with that is your business. You're welcome and appropriately or legally permitted to go right that the answer for FG is a minus 500. But the number of people, students and practitioners alike, who'll miss the minus on there later on are numerous. I'd really suggest if you find an arrowhead wrong, you don't have to tell everybody. Just go put it on the other end. And then no one will ever know you're not good at guessing arrowheads. And then it kind of makes sense, since this thing goes up, this guy probably does go down. And then you need to go change your sign, so if the guy actually checks your work, he doesn't see a plus where the force is going down and count off. Change the sign for FG. That would change the sign for the answer. And that means leave the arrowhead alone. And it also means that the force, since it is pushing on G, is a compressive force. Most especially in this class, it tells you that the force will be getting shorter or longer. Lane, which is it? Will the member get shorter or longer? Shorter. Look at that. What a good guesser he is. He had no idea in the world. You can put your quarter back in the pocket, back in your pocket. Came up heads, and it served you well. Being in compression, the member does get shorter. Do I care if you sleep? Well, not really. I mean, I hate to admit that. Do you bother me? You really don't. But I'll tell you, I only got through one class because the guy was merciless with me. He would throw stuff at me. He'd stick chalk up my nose. And that's the only way I ever got through that class. So I'm going to try and do that with personal friends like Lane. Who was the other one? I forget. All right, so now then we have that force. Thank you, ma'am. Equation 2 reads, some force is horizontal is equal to 0 is equal to, and yes, I know, you're bored, I'm bored, minus hg plus, so I wish I had listed that answer on the free body. It would have been smart, because then I wouldn't have thought it's unknown. And I should go do that now. 500 kilonewtons. I probably wouldn't put compression on this because it is shown pushing in compression. Plus Fg, which is 500. But not all of the 500 points in the horizontal direction. McMahon, how much of the force points in the horizontal direction? Oh, McMahon's not here. Look at this. Right off the bat, I found somebody not here today. 9408, McMahon, 2. Garza. If you're next to somebody who's not there, you're usually a pretty good chance of being asked. Do you know the answer? Don't feel bad. I don't remember the question. Mr. Condit, did you happen to save both of us by remembering the question and the answer? No. All right, well, let's see what we would. Oh, yeah, I was asking you how much of Fg points in the horizontal direction. Now, that really is not something that everybody ought to know that. You really should. The horizontal component of this slope triangle, which is a 3, 4, 5 slope on the triangle, is in the same proportion as to the components of the load. So Fg does point to the right, hence the plus, but only the horizontal piece of it points horizontally. In other words, 15 out of the total of 25 available. Now, if you may not have done it that way. You may have gone and said the tangent of this angle is 15 over 20, and wrote the angle in there, and then multiplied this times the sine of that number of degrees. You're welcome to do that if you want to, but that's a long, hard way to do business. Morales, how would you do it? Mumble, mumble. So that's an old trick. You mumble, mumble, and the guy, you know he's old and deaf and can't hear, and they say, that is correct. You would multiply it times 15 over 25. And you say, thank you, Lord. I know. Man is equal to 0, and so we ought to be able to solve for the force in member HG. Force in member HG is whatever it is. I have little interest in it. It's a calculator problem now. The minus sign is going to turn around to be plus on the other side, leaving this as a plus, so it will turn out to be appropriately shown. The arrowhead does not need to be reversed. It is a tension force in the member. Now, the only other thing I would do is I'm going to go ahead and show you a free body for joint F, just to make sure you know what to do with what you've already solved for. This is an exercise in futility, because cutting joint F has exposed 1, 2, 3 new unknowns. Even though that one is now known, that means we were not going to get answers, but at least I want to make sure you can properly draw the free body. Here would be free body 1. Here would be free body number 2. Here's the piece of steel. It was marked F on the end of the pen. You cut this piece of steel open. It is your choice. Pick an arrowhead. I will tell you that for most trusses normally loaded, the entire top of the truss goes into compression, and the entire bottom goes into tension. That's normal. Other loadings can cause other kinds of things where that doesn't turn out to be the case, and you shouldn't get so enthralled with it that when your answer comes up with a minus sign, you don't listen to the minus sign. Yes, sir.
For the homework problems on method joints.
Yes, sir.
If I were to write a MATLAB program that just solved it, can I hand them the code?
Not really. And the only reason I say that is because everybody already has access to a structural analysis program called visual analysis. Some of you have already learned how to use it in other classes. And then I'd really have to say, well, it's okay just to stick it in visual analysis. The real problem is when you get in here, you're not going to have that available to you. If you say, you know, when I get in here, I already know how to do that, and you're just wasting my time, I have to apologize. You may be right. There may be some truth there, but I don't know how to really make everybody do this except by hand at least once in their life. Okay? All right. So your choice. I'm going to show it pushing just because the top of most trusses are in compression. I'm also going to give it a name. Its name is EF. I have also cut this member here. His name is IF or FI. I do not know which way he goes, and therefore I'm going to absolutely guess. Well, I didn't know which way this one goes either, so I'm guessing both of those arrowheads. Then I cut through FH or HF, depends on whichever one I wrote first from another free body. I wouldn't really want to call this force in this member FH, and then in my work call this one HF. They are, of course, the same number, same answer, but you're liable to get lost in that somewhere, whatever you call it. If you're going to call it FH now, later on you ought to call it FH again. This guy is FH. That is an absolute guess. And only on the next one, FG, are you stuck. You have no choice. On this one, you must show it as a pushing arrowhead, because that's the truth. That's the first truth we found this truth, but that's truth. And therefore, this one is required. And I don't know how. Maybe I'll just put several arrowheads on there. I mean, there's no question about that. It's got to be shown as a pushing piece of steel. Now, if you say, well, wait a minute, you showed it down on this one and up on that one. No, I didn't. I showed it pushing on this one. And if his feet are pushing down on this joint, his hands are pushing up on that joint. And then, of course, it has the name FG, because that's what I named it earlier. I don't think calling it GF is a wise move at all. The final thing this needs to be a free body is this needs to have a slope on it. It's poorly drawn to scale. That's a 15 by 20 by 25. You could go ahead and revert that to a 345 if you want to. And this one also has the slope 345. You would then, some forces horizontal, some forces vertical. You would, of course, find that you cannot solve for all the forces because you have too many, and we knew that was going to happen. Now, some of these members can be found by just looking at them. You can just tell what the force is. Here's an example. Well, let me show you a more general thing, and we'll go back to this. Here is a member, and here is another steel member, and they are collinear. They are pinned on the ends, and they are pinned together. And they're supposed to be straight. Normally I wouldn't care about slight discrepancies like that, but I really have to emphasize the fact that those two members act along the same line. And I don't care if that's okay, that's okay, that's okay, that's okay. I don't care how they're sitting in the structure, but they're in a straight line. And if anybody comes in, a third member comes into a pair of collinear forces, or collinear structural members, the force in that member must be zero. This is called a zero force member. And the reason is, I'll let you put any force you feel like you'd like to. You say, well, okay, I'll just put 100 pounds. Then if you put 100 pounds, then you're going to have 100, let me put a theta right here for an angle, then you're going to have 100 cosine of theta acting on the joint because of this guy, and you're going to have 100 sine of theta acting in this direction. And now you can throw away the original member. This is unacceptable. You have a force pushing up, and you have these two members. Here they are right here. One of them is doing this, one of them is doing this, and here you are doing this. There's no way that these two horizontal forces can take this vertical force because they don't have any downward pointiness to them to accept that. If you some force is vertical right now, some force is vertical is equal to 100 times the sine of theta minus not me, minus not me. Nobody can take that vertical load. You say, well, okay, well, I don't put 100. I'll only put 1. I don't care. I don't care if you only put 1 eyeball of a fly. You can't take a component normal to those two members. So I'll tell you now, if you ever see a structure where there are two collinear members coming in, let me clean it up a little bit. If you ever see two members coming in collinear, and there are no applied forces, if there's applied forces, this rule is gone, it drops off. But if you see two collinear forces, if you see a member coming in, it has no force on it at this time. Now, a lot of people say, well, what's it there for? Why did we buy it? Well, later on, when the loads move around to a different spot on the truss, it may well be used. But right now, it's got no force. A corollary to that, or a simplification of that, is listed in our book first. If you ever have a member with another member coming in like this, and there's no force on the joint, we only put the forces on the joints, then those are both zero force members. The reason being, if this force had any force in it, if this member had any force at all, it would have a vertical component. If it had a vertical component, you could not stop the sum of the moments about this point because that force acts right through this point, so that's zero. And by the same token, If you had this member and you're trying to see how much force is in this one, if I let you put a pound in there, it'll have 1 pound cosine theta, and that will cause rotation about that point, and that's not permitted. You can also look at it as this is the same as this. There used to be another member here, and there are your 2 collinear members with somebody coming in at an angle and no other forces acting on it. That's a 0 force member. You say, well, but there isn't one there. Well, it's okay with me. The rule still applies. Just because you took away that member, you just made it even more 0. And by the same token, here are a pair of collinear members. If you don't want that one in there, if you want to take it off, that's acceptable too. Here's a pair of collinear members with somebody coming in at an angle. That's a 0 force member. Hence, you'll have to hey me a few times here. Give me a 0 force member.
BG.
Baker George. The rule won't apply there because on this end of BG there is a force. So sorry, I'm not sure I emphasized that enough, but those forces make the rule go away. Hang on. But you might say, well, check the other end. When you check the other end, the rule is broken because you do have another member coming into the joint. DF, I agree. DF is a 0 force member. The reason is it's coming in, it looks like it's coming in square with those other 2, but I don't care if it comes in square or not. If it comes in to a pair of collinear members, there's no force in that member. Now I would say, well, then how about this one? But the rule breaks down because there's a force here. How about this one right here? Give me a 0 force member. Dog, fox. Now, because that member is 0 and could be removed, DG. That's correct. And who else? BH. That's correct, because on this end there's a pair of collinear members, and so that's 0. And I believe at that point the rule falls apart, because if you try for Charlie George, down on this end it's a mess. There's all kinds of stuff going on down there. Can be no members coming in and can be no extra forces coming in. All right, how about this one? This is the one I got? Yeah, this is the one I got. DH, BH. I like BH, not because of the top end, because of the bottom end. Now, students will look at that all day long and say it's impossible. Where did that force P go? Well, I don't know, but he didn't go down BH, because on this end of BH, these people can't support him. So there's 0 force in that member. So where did this go? Well, I guess it went down this side and went down that side, because it didn't go in BH. And I don't personally see any more of myself in there. How about this one? BG is good. Keep going. DF or FD is good. And I think that's about all you're going to get. GC, those do start becoming obvious. AB is good. And AH. And again, if you want to pretend that this member AH has a buddy sitting out here, pair of collinear members with somebody coming in, it's 0, and then you can throw it away and the rule doesn't change. It's just that member is also removed. And then by the same token, if you say, here's the member I'm talking about right here, and this is the guy coming in at an angle, the other one is 0. And I don't see any more. EJ, BJ, I buy, BJ. HF, very good. EH, now wait a minute now, there's a bunch of members coming in here. Let's check the other end, he says. Okay, I checked the other end and you're right, because this is a member coming into a pair of collinear members, EH is 0. DH is also true because now EH and FH can be erased, leaving DH as a single member coming into a pair of parallel members. And of course the question definitely becomes, what's all that steel for? Well, when these trucks get around on this side, or I guess they're heavy birds or something on the top of the truss like that, they will be used. They're just not being used now. BH, I buy that. DF, I buy that. DG, because you can now erase DF, DG becomes a zero force member. That's correct. And one last one. DF, CF, CG, BG, HB, and AH. That's true. They're all zero force members. They have no choice. You're welcome to solve for them if you want to, but it takes a lot of time. And on the FE exam, you don't have a lot of time. And they love zero force members on there because they figure you ought to just be able to go point them out. Now, if you say, well, where's the force going? It's evidently going down this member in compression and probably pulling on this thing in tension, and these right now are not being used. When that force P is back here at this joint or this joint or this joint, they'll start being used, but not right now. All right. The second method of analysis, you can use the method of joints all over the place. You can follow from joint to joint to joint to joint, and you can usually get answers all the way across the structure. Every time you move to a new joint, you do take a chance, because the first time you made a mistake, that mistake's then going to follow you along through all the other equations that you have. Hey, thank you. All right, here's the structure. Well, we'll just do one kind of like we did before, be okay. Okay. Now, if I ask you to solve for the force in member DE, to get there by method of joints, it would take a while. You'd have to start out here at G or A. Without a doubt, you'd start at G because it's closer. G because it's closer. But it'd still take you a while to work over there. Method of sections has the advantage of you can usually get an answer immediately. Plus the second advantage, it doesn't depend on much previous work. Now, if you have these reactions wrong, well, then obviously you've got a problem. To get the force in a member, for example, DE, you cut through DE. That exposes the force you're looking for. You then cut on through the structure as inexpensively as you can, cutting as few additional members as possible. hopefully 3 maximum total, because that even now that's all the equations that you have. And you draw a free body of that substructure. That substructure looks like this. There's joint E, there's joint F. Here is each of these members approximately cut in half around the middle. Here are the loads. Here are the slopes. The only ones I care about are the ones that are exposed. That's a 3, 4, 5 slope. My guess on arrowhead on this one will, if it's on the top, it'll always be compression, as it usually is compression. I will not get so attached to it that if the answer comes out minus, I'm not willing to change it. And it has to have a name, DE. I have no idea which way this arrowhead goes. Anybody want to guess whether it's a tension or compression arrowhead? Tension, so we'll show it as a tension arrowhead. His name is DI. And finally, these on the bottom are usually tension. And his name is JI. It has to have a name. It's free body number 2. Why is it free body number 2? Yeah, because the whole thing was free body number 1. That's where I got the reactions from. Have to have dimensions. You can pick them up from the original diagram if you want to. 15 meters. They're usually worth the effort to go ahead and draw them on the free body itself. So, now it's a free body. Now it's soup. All of the cut members have arrowheads, guessed, and names. Anything that's been cut has got a slope on it, so I can get components from it. Everything else, for example, reactions or loads that are inside that free body are shown on the free body. And nothing external to that free body is shown, because you're supposed to be able to make that little set of steel bars sit still just from the things that you see in the free body. You shouldn't need any outside help. Now I asked you to solve for DE. And therefore, you like DE. Why do you like DE? Because the guy's willing to pay you to tell him the force. And remember DE. Who do you hate? I really hate DI, and I really hate JI. The reason I dislike them so intensely is I'm not being paid to find them, and if it wasn't for them, I could just sum forces horizontal and get me an answer and go home. So what I do is, same thing you do if you're mad at 2 people. You wait till they meet at a bar. You take your big stick and you go to between where their seats are, and you sum moments. And that gets rid of both of them right off the bat. Boom, they're gone. They're not in your equation anymore. So the rule is, if you want DE, find out who's stopping you from a quick and easy answer. Follow them until they meet at a point, and wherever they meet, sum moments about that point, and they will have no moment arm, and so they'll drop out of that equation. So the equation reads, using free body number 2, my first equation is well, actually I probably already had 3 equations up on the first free body. It's probably about the 4th equation, unless I did some free bodies of joints, who knows. Sum moments about, this is point I. Now see, that's what happens when you go to sleep. Somebody help him off the floor. Sum of the moments about point I is equal to 0 is equal to, first I see a 400 kilonewton force. Summing moments about I find out how long it is to tie a piece of string to him, to as close as that string ever gets to his line of action. That's 30 meters. And then I kick him off of joint G and let him start rolling. The string gets tight, and he starts rolling this way about joint I. Since that's the way my right hand is made, I normally call that a positive tendency to roll. It's up to you. You can use any sign convention you like as long as you're consistent. Phooey. Next, I see a 600 kilonewton force. What's its moment arm? Therefore, I won't bother writing it down. Next, I see DI, no moment arm. JI, no moment arm. And then DE comes into play. Here's DE. He has a 20-meter moment arm. His tendency to roll, should he get away from you, and should that arrowhead be on the right end, there's a bunch of ifs there, would roll not the way your right hand is made. That would be called a negative tendency to roll. Therefore, I can solve for the force in member DE is equal to 400 times 30. The minus comes over as a plus. That stays as a plus. Divided by 20. And I don't know what that is. Well, yeah, sure, 20. 600, thank you. 600 kilonewtons. And since the arrowhead does belong on that end, that means that that is a compressive force pushing on the joint. Now that's pretty slick. I got you an answer way out in the middle of the structure. You didn't have to walk there a joint at a time. We'd have been there at least till class was over plus 20 minutes getting there. And it'd be wrong because we'd get one of the components wrong, just sure as can be. This depends on nothing else. Method of sections. Equation 5 reads, now let me do this here. Let me add to solve for the force in member DE. You should sum moments about I. To solve for the force in member JI. Yes, sir.
How is that DE is in compression and not tension?
Well, from looking at the whole thing point of view, when you pull down in the middle of a beam, the top of it gets shorter. In other words, you're trying to pull it between the supports, and the little piece on the bottom tends to get longer because it has further to go. So that's why from that point of view. From the point of view of you guessed the arrowhead as compression and turned out to get a positive answer for the result, that it's compression for that reason, because it is guessed pushing, turned out it is pushing, and therefore it is compression. You can also see when you sum moments about I, see how this guy wants to do this? Well, this guy has to resist that bad attitude. Now, I'm not sure that's the answer to your question, but by now you've usually forgotten it, so I'm usually okay. Is that okay? Well, come see me, and we'll look at it more if it doesn't make sense. Because those are the basic kind of things that if you say, who cares, man? Why did the guy ask the question? If you're not curious and you don't wonder about these things, you're not going to make a good structural engineer. You'll be one, but you won't be a good one. So come see me. To solve for the force in member JI, who do I like? Now, where's the money? JI. Who do I hate? Everyone else. That's true. I hate DE. You know, we really probably should have listed that answer as soon as we found it. 600. Probably wouldn't write compression on there because it's shown compression. Yeah, I hate DE and DI. You say, well, rather fickle, aren't you? You know, a minute ago, you liked DI. Well, 10 years ago, I liked my wife, too, but you know, these things happen. The reason I don't like it now is, first place, it could be wrong. In my case, incidentally, she always was wrong. And if it's wrong, that'll influence this answer here. I don't like that, and I don't like that. And so what am I going to do? Something ugly. What? Well, I follow them until they meet at a point. You know, I worry about you. There are much more acceptable ways of settling those kinds of disputes. I'm going to sum, you can even tell where I'm going to sum moments about, because the two people I don't like, they have the same first name. I'm going to sum moments about D. Summing moments about D will get rid of these two people that may cause grief, leaving only this person hanging out in the free body. To solve for force in member JI, comma, sum moments about D. And so we sum moments about D is equal to 0 is equal to, we see a 400 kilonewton force. We notice that if we tie a string, here's the string, you'll see it looks wiggly. Here is the line of action of the force. Beep! There's where we tie it to that point right there. That's the moment arm. That's the shortest perpendicular distance between the force, the line of action of the force, and the point you're summing moments about. And that's 1, 2, that's 3 15-meter numbers. 3 times 15. And his tendency to roll, once loosed and the string gets tight and it starts to roll about F, would be this way. Would be this way. That's a positive tendency to roll. Next, I see this 600K force. I list it without respect to up or down, right or left, minority, non-minority. I just write the number down. Next, I find out how far it is away from the point I'm summing moments about. In order to do that, I get on this train. It's like you get on the railroad tracks, and you huff and puff along until you get as close to this point as you're ever going to get. And therefore, I go up here, I go up here, I go up here. That's as close as you're ever going to get. The length of the string to be tied to it is 15 meters. So it has a 15-meter moment arm. Were he to get away from you, tied back here to this string, he would roll that way about point D. That's not the way my right hand is made. I'd call that a negative tendency to roll. DI has no moment arm. DE has no moment arm. JI is all that's left. There's JI. His moment arm. Tie a string to him as close as he ever gets to you. As soon as he comes past, tie a string to him. The length of that string is 20 meters. 20 meters. The tendency to roll, should he get away from you, tied to the string, if you don't see these, you need practice, is a negative tendency to roll. And from that equation, we can solve for JI. Equation 6, this is easy. To solve for the force in member DI. The only reason I'm solving for those particular member forces is because they're the ones that were exposed from the only free body that I've drawn. Who do I like? DI. Who do I hate? DE. Who else? Here, let me ask my old friend back there, Lane. Lane, you're going to have to learn to sleep without laying your head in your hand. You don't have a prayer. No, it's okay. But yeah, I'm picking on you, but it is okay. But I'm probably not going to get an answer out of you for a few minutes here, so let me pick on somebody else. Somebody point to somebody who's sleeping regularly and we'll get him. No? All right, Lightfoot, sorry, can't find any more sleepers.
Solve for DI?
Yeah, I'm looking for DI, and I like DI, and who do I hate? Anybody else that's listed on the free body hanging out, I don't like them. The only reason I even like this guy is because there's a dollar mark attached. No. Yeah, probably, but I want you to tell me if I like this guy, who do I don't like? Baker? Right. See, Lightfoot, what she's saying is, you like this guy, he's exposed, you like him because they'll pay you to find the force in this member. This guy here is also hanging out, and you say, well, you know him. Yeah, but he could be wrong. And this guy's hanging out. Anybody hanging out, but the guy that I'm looking for, I don't like him. I really don't. Those are the people I'm trying to get rid of. Now, maybe it sounded like that's what you were going to try and do, is get rid of them. The rule is, anybody you don't like, follow them until they meet at a point, and some moment's about that point, and they'll drop out because they have no moment arm. Winfield, can you follow these two until they meet at a point? You can't, can you? They meet at infinity down to the right or down to the left. Well, anytime that rule breaks down, follow them until they meet at a point, and some moments about that point, that means you get to drop back to one of your easier equations. Some force is vertical, or some force is horizontal. Now, if you sum force is horizontal, I forgot again to write this answer. Well, we never found that answer. Did anybody happen to solve for it? 450, thank you very much. Did it turn out to be tension as shown? Yes, okay, thank you. So 450. Now you say, well, I don't know why you don't just go ahead and sum forces horizontal. Nothing wrong with it. Plus 600 minus 450 minus this guy's horizontal component. What's hard about that? Nothing. The only problem is if that's wrong or if that's wrong, then you got another wrong answer. Usually you can find one of those equations where these other people will drop out. If they don't meet at a point horizontally, that means they're acting horizontally. So if you'll sum forces vertical, you really get a quick and easy answer. To solve for DI, sum forces vertical equals 0. And so then we simply sum forces vertical equals 0 is equal to minus 600 plus 400 plus DI. Booth? You happy with that? Is it finished? Oh, you want a factor applied to this? Why do you want it? What's the factor going to do? What's it for? Very good. DI doesn't act pure up and down. Only a piece of it acts up and down. Did you say 3/5? Okay. Times 3/5 times 4/5. That's probably what you said. I just wanted to make sure you were seriously committed to 4/5. The reason it's 4/5 as opposed to 3/5 is you're not looking for the horizontal component. You're looking for the vertical component. And you solve for the force in member DI. And now this one is going to come out tension, actually. And if we'd have thought about it, we could have pretty well determined that before. You see the 600 is beating up on the 400? You see how this guy is winning? There are no winners in statics. This guy needs help up. And so that arrowhead doubtlessly does go up. All right. Seemed like last time I asked what time is this class over, and somebody told me now. Then I got home and realized you lie.
That was your 305 class.
Was that my 305 class?
Yeah, I was sitting in on that.
All right, okay. All right, so you should be able to do that. Let's try one. Pop quiz.
Is it supported by anything on the other side?
Yeah, no, these are the supports on at A and F, and I went ahead and gave you the reactions, and this is one 300,000-pound truck called a uniwheel truck. And I'd like for you to solve for the force in member DH. You can work together on pop quizzes. I admit it may be embarrassing to ask the guy next to you for help, but better than not getting a good grade on a pop quiz. Which side would you circle, the left side or the right side? The right side, I kind of agree. There's only one thing over on that side. Not that circling the left side would be any much more difficult. I want you to solve for Dog Henry. This one right there, that slanted member. If you were not on this seating chart, I need to know about you because I don't know that you're in the class. I don't have a record of you. What took you so long? Kips, yes. Sometimes kilonewtons and sometimes thousands of pounds. Now, hang on a second. Did anybody else get 180 kips of tension? You want to wait a minute and just make sure you got it right?
It's 100.
You know, I don't see, I won't say this number's wrong, but danged if I see how. You see how you don't have a slope shown on that member? I mean, I'd sure fear.
10 to 18.
Well, yeah,
It's
well.
18. So 10 to 18 is 100
Oh, wait a minute now.
to
Are you telling me that member is a 10, 15,
number.
18? This one?
number's 18.
Is it really?
Mhm.
Gee, that's unusual. 10, 15, 18. I didn't know there was such a thing. I know I've heard of a 5, 12, 13, and a 3, 4, 5. Is that the right length of that member, 18? Get out.
18.03.
Oh, is that all it is? Is that all it's off? Well, I don't mind those kind of things.
Yeah.
Okay.
If it's 10 to 18, right? And then if the 100 is left over from.
Yeah, man, I don't know. I'd put the slopes on there, and I would put that this side is 15, and I put that side is 10. You don't even have an equation. Here, let me help you here. Here, let me help you. Some forces. No, it's too late now. Is equal here. Let's cover up your name because that would be embarrassing. Is equal to plus 200 minus
I'm gonna be the
300
last person out on the rotation.
plus DH, but we don't want all of DH. How much of DH do we want?
10 to
10
18.
18ths. All right, well, you may be right. It may come out. That may be what it is. Did you get 180?
180.3.
No, I don't care about that. All right, you were right. Listen, I want to see equations from now on, okay?
Now, my question earlier
Tension, yes. Yes, sir.
was you called this in compression?
I called
Go.
this
Okay.
in
That's-
compression.
that- okay,
I don't
that's-
know this guy and I don't know that guy.
Okay, but you were going from this point.
That's correct. Well, it's not a matter of going from this point. It is that this was shown pushing on the joint, and that makes it compression. And if
See, I
it,
thought that this was tension and then that was compression.
well, this is tension on the member, but look what this tension in the member does to this point.
Okay, so we're talking about at the point.
Take your choice. In other words, pulling on the joint means pulling on the end of the member. That is tension. And now then, that is, you see how that's pulling on the joint? That's tension. And you see how that's pulling on the joint? See, you showed me the joint.
Yeah.
And so that's tension.
Okay.
And as a matter of fact, if you had somebody, well, we just had that right here. Somebody pulling on the joint. That means the joint's pulling on him. That's tension. Now let me show you a member that's in compression. See how someone is squashing it, making it shorter?
That's how you draw it.
That's compression. But what does the member do to the joint? That's right.
Okay.
And what is it? There you go.
Okay. Well, that's.
All right.
I just made sure.
All right. For today, well, you've been back there working this all this time? Well, you got to hand this in at the beginning of class unless you want me to write late on it. Now you know. Oh, well, no, I want you to be rude. Because otherwise, these bozos will sit back there and copy each other's paper and hand it in after class. All right.
Were we supposed to find the homework assignment on your website?
Yeah.
On CE notes, I couldn't find it.
No, I'm sorry. I understand. No, the problem is that, wait, what is this? Are you Morales? Are you Garza? Where's Morales? All right, you're not just handing in something for him, huh? It's on my website, lowry.tamu.edu. I know most all the profs put their stuff on CE notes. Mine just happens to be where I can get at it.
Well, I found the first one on there, so I didn't even realize there was an assignment due.
They're all of them. Put a note on there and say, I didn't realize where to get the homework problems, and I'll sign it when you bring it.
Yes, sir.
But once only.
I'm in the same boat as he is.
Oh, I don't believe that. No, only one guy could be that could.
CE notes.
All right, same thing.
Thank you.
Sure thing.
I was wondering, how come on the windward side of the
Yeah.
building, the force is different, but on the leeward side they're the same?
That's a little hard to explain, and there's a lot of theory involved, and I'm not a wind guy. But basically what happens is when you have something in the way like this, the fact when it's down at the ground, the higher up it is, the more and more pressure you get, and that kind of makes sense. But this wind that's going around is the same as this wind that's going around, and so you get the same suction all the way up.
Okay.
Now, if it were not true, I would not tell you so. And the same way in the back, you get the same suction back here. I imagine the first guy that put a little pressure transducer back here said, "You must be kidding. This thing is 200 feet in the air, it's got the same suction at the top as it does on the bottom." And the guy writing down the data says, "If you don't like it, we can lie about it, but I don't know what else to tell you." So we're kind of in that boat. Okay?
I was sick on Tuesday. I have a note.
No, I don't need that.
No, but for the pop quiz. But I
Okay. We had another pop quiz in here?
Okay.
I'm asking, did we have a pop
On
quiz in
Tuesday,
here?
Yeah.
Okay, well, remember what it was?
No.
I don't remember what it was.
Getting a pop quiz out of the
Oh, getting out of the thing. All right. Got a piece of paper?
Oh.
Give me a piece of paper. All right, that's fine. Here, I want you to solve for the force. This number right here is 60 and got a slope of 5 by 12. This one's got 200. This one's got 80. And this one, I don't know. And it's sitting at a 345 angle. And its name is Joe. I want you to solve for Joe. You can hand it in next time if you want to. Or write pop quiz on, or make up pop quiz on it. Put your name on it and then give it to me next time. What took you so long?
I was in the bathroom.
Oh, all right, okay. Nope, that's wrong. And I got a bunch more here that are wrong too. Tension or compression?
Oh, okay, I didn't know that.
It's important.